expression. So I could say, for instance, so this is an example of a formula in DNF, right? So obviously, we don't talk about satisfiability of DNF is not very hard, right? So how do you find a satisfying truth assignment for a formula in DNF? Right, so any one class, you make it true, and so it's trivial to find a satisfying truth assignment for a DNF, right? So can you think of a problem that's actually hard for DNF? A problem similar to satisfiability that is hard on DNFs. Tautology? Is that what you said? Okay, so whether this is a tautology, that is a hard problem for sure. But it is actually, as far as we know, it is actually harder than the satisfiability problem itself, right? Because we'll come to that in a couple of slides. Something that's as hard as satisfiability. See, obviously these what is AND and what is OR, right? They are somehow duals of each other, right? So if you can if all you have done is interchange AND and OR, then there must be a way to find the dual of this problem, which is going to be hard on DNF. So what is the dual of this problem?
Negating each and every term, like converting AND to OR and OR to AND, and negating each and every term on each.
No, see, these are two different formulas, okay? They have no relationship. I just didn't want to construct one from scratch, so I just, did some, but these two have no relationship to each other. One is true, truth assignments that make one true have not a whole lot to do with the truth assignments that make the other one true. So obviously, figuring out whether making a DNF form true is easy, but making it false is hard, right? So because in order to make it make it false, you have to make each one of those false, right? And then you are essentially in the same situation as making a CNF true, right? So it's not that CNF is somehow distinguished and we have to work only with CNF. We could equally have worked with DNF and ask the problem of, is this DNF unsatisfiable? Okay, and that would be equally hard. Okay? So what do we cover under NP? We only deal with decision problems, not with optimization problems. Okay, so we often, if we have an optimization problem, we turn it into a decision problem where the answer is either yes or no. Right? So we don't say, okay, find the shortest path. Instead, we would say, is there a path that's shorter than a particular length? Okay? So this is how we convert optimization problems into decision problems. Okay? And then, well, this means that you have to give an estimate for that value, right? So then you can recursively refine that value using something like a binary search. So even though, so in general, optimization problems can be solved only with another factor of log n or something like that, once you know how to solve the decision problem. Okay, so that's why it's we primarily work with decision problems in NP. Okay, so again, the definition of NP is such that the non-deterministic turing machine is going to guess a path to a solution, and it's going to give you that path. And essentially, you have a way of verifying whether that is actually a correct solution or not. Okay, or if let's forget the Turing machine and just think of the guessing part, right? So there is a guessed answer and then there is a verification part. Okay, so whenever you're asked to prove that some problem is an NP, okay, so then what you need to do is you need to say, okay, let's say we can guess a problem, guess the solution, and then you need to say, okay, here is a way to verify the solution in polynomial type, right? So again, polynomial verifiability is the key for NP. Okay, but when the answer is no, okay, then you may not be able to verify that in polynomial type. So for instance, if I said this formula is not satisfiable, okay, so how can I prove to you that it is not satisfiable? Because that requires me to consider every possible truth assignment, right? It's not like I just guess one, right? So to show that it is satisfiable, I just have to tell you a guess for which variable to set to true, right? Once I say that, you can immediately, very quickly substitute those values and check whether the whole formula is true or not. But if I tell you I can't give you a satisfying assignment, there is no way for me to give you a compact proof, polynomial size proof, that actually shows that in fact there is no satisfying assignment. Okay? So that's another property of NP problems. Okay, when the answer is no, you are not able to give a compact proof. Okay, so again, we know if you think about finite state automata, again, if it's a non-deterministic finite state automata, it's easy to negate. You just make, final states into non-final states and non-final states into final state, and now you have the negation of the automaton if it's a deterministic automaton. Okay? For a non-deterministic automaton, there's no easy way to negate, and in fact, the only known way of doing this is to convert the NFA into a DFA and then negate it. Okay? And once you do that, well, obviously, you are in going from an NFA to DFA, you are causing an exponential blow up, right? So what that tells you is that negating NFA is not something that you can do very efficiently, and the same kind of idea comes up here, that you have these NP problems which can be where if the answer is yes, you can verify the answer quickly, but if the answer is no, there's no easy way to verify. Okay, so this comes back to this issue of existentially quantified versus universally quantified formulas. Okay, so if you think of the satisfiability problem as a formula in first order logic, then what we are saying is there exists some value for x, y, and z such that this formula is true. Okay? Now, when we want to say that this formula is unsatisfiable, then what we are trying to say is for all values of x, y, and z, this is unsatisfiable. Okay? So again, if the formula is existentially quantified, then you can use this idea of guessing a particular valuation for these existentially quantified variables, substitute, and then check. You got polynomial verifiability. But if you have a for all problem, then at least intuitively the only way seems to be to systematically try out every possible value, and that cannot be done very quickly. Okay? So, and then again, of course, you all know that, right, exists is the same thing as, not for all not, right? So, when I say there exists x, that's the same thing as saying, not for all. So what this means is that whenever I negate a there exists problem, right? So that means, so whenever I negate a problem, right? So that means I have a for all problem. This is why when I take an NP problem and then I say there's no solution, well then whenever I say there's no solution to an NP problem, that's equivalent to proving a for all formula to be true, which means that I need to somehow try every possible value. Okay. So this so we talk about these problems unsat and valid. So the valid, which is the tautology problem, right? So if to show that a DNF is valid for all possible truth assignments, again, it's a for all problem. It's not in NP. Okay? Same way to show that the CNF formula is unsatisfiable. That's again a for all problem, and so it cannot be solved. So anyway, the idea is that at least intuitively it seems that these for all problems are even harder than the NP problems. So that's why NP is a useful intermediate step which tells us, okay, here is a class of problems for which at least if I assume that there is this way to guess, I can solve it from there. There are for all problems where even if I had this oracle, I still would not be able to solve the problem fast. Okay, so because we talk about this, original problem and the negated problem, that brings us the notion of co-NP, which stands for complement of NP problems. Okay, so if a problem is an NP, then the complement of the problem is going to be in co-NP. Okay. Now, of course, the class of problems that have polynomial solutions, right? That means that you can solve them in polynomial time, regardless of whether the answer is yes or no, right? So you have a polynomial time solution, it's going to work. Deterministic polynomial time solution, that's going to work no matter whether the problem is, whether you have a positive formulation of the problem or negative formulation of the problem, or in other words, regardless of whether the answer to this problem is yes or no, you're going to have the solution in polynomial time. For NP problems, if the answer is yes, then you can verify that in polynomial time. So that way you have a non-deterministic Turing machine that can solve the problem in polynomial time. For co-NP, it's the complement of NP, which means that the negation of a co-NP problem can be solved quickly, which means that if the answer to a co-NP problem is no, right, then you'll be able to solve it fast. But if the answer is yes, then you will be able to solve it fast. And of course, one of the biggest open problems for which there have been a number of so-called proofs, which prove to be wrong, is this problem of is P equal to NP. And if P equal to NP, then of course what that means is that everything in NP is solvable in polynomial time, which means that whether the answer is positive or negative, or whether the answer is yes or no, you still will solve in polynomial time. Therefore, co-NP will also collapse to P. Okay, so one of the things is that there are, so in the previous picture you did see one interesting point, that P is the intersection of co-NP and NP, right? And the question is, suppose there is a problem which is in the intersection of co-NP and NP, right? Which means that it's over here, right? If it is in this region, does it imply that it might be actually a polynomial time problem? And the answer seems to be, at least in terms of experience so far, it looks like most of the time when you have a problem that's both NP and co-NP, it tends to have a polynomial time solution. Okay, so let's take some examples. Okay,
excuse me.
Yeah.
Why is P a subset of NP in that earlier slide? Like, how can a problem be both P and NP?
Because if you don't need any guess, then it's a problem. The problem has a solution in P time, right? So NP means you also have the ability to guess, but you can not use that ability to guess, right? Or think of the non-deterministic Turing machine. It has more than one possible transition at every stage. But if it has only one transition, that doesn't make it a invalid non-deterministic Turing machine, right? So it's just that it's strictly more powerful, right? The way NP is defined is it's already defined as a superset of P. So let's take some examples. Okay, so linear programming was an example where how do you know that it is an NP? Okay, so you know that it is an NP because, well, you take, again, remember, it's a decision formulation of LP problem, okay, which means that does this optimization, is there a setting of values to these variables so that it satisfies all the constraints and the value that you want to optimize is above a certain value, right? So there is always an objective function, right? If the objective function is above a particular value, that's how you make a linear programming problem into a decision problem, is by saying the objective function should have a value greater than x, right? So some value x. So to see that if it's an NP, you just have to guess a value for these variables, check that all the constraints are satisfied, right? Checking that the constraints are satisfied for that value is easy, right? And then you also evaluate the objective function in that at that particular value of those variables. So it's easy to check, right? It's easy to check that the solution to an LP problem is valid. To see that why it's co-NP, right? So if you're told that the question that's being asked is that is there a way to get the objective function to be, let's say, above 100, right? So the answer comes back, no, there isn't a way to set the objective function above 100. Well, can you verify that also in NP time? Remember, in LP we had this way of combining the constraints in some form to show that the solution is optimal, right? So basically what that combination of those equations said is that there is no way to get the objective function above a certain value, right? And in order to get to that optimality proof, what did you have to do? You needed to guess some multiplier for each of the constraints. And you guess this multiplier, add them up, and then you will be able to show that the objective function cannot exceed a certain value. So again, all you need is this ability to guess the multiplier for each of those constraints, right? And once you do that, you can that way verify that whenever someone tells you that there's no way to get the objective function above a certain value, you can easily use an oracle to give you a proof that it cannot be above the value, right? So it's an example of a problem that happens to be both in NP and co-NP. And so that got people thinking, and they said, well, there must be a polynomial solution, or there's a good good chance that there is a polynomial solution, and in fact, the polynomial solution was found in 1979, long after the exponential simplex method was found. Okay, primality testing is another example of a problem that's both in both an NP and co-NP problem, right? So if somebody tells you that it is not a prime number, right? Is that an NP? Suppose I ask you to show that, I give you a prime number, or I give you a number, right? And somebody tells you that it's not prime. Now, to show that it's not prime, can that be done in NP time? How would you do it? So what guess can you make that will allow you to prove that a number is not prime? You just have to guess a factor, right? It's easy. There's nothing to, there's no, right? It's very easy. You just have to guess a factor and you verify that this factor actually divides it. So once again, if you have this magical ability to guess, it's very easy to verify that some number is not prime. To prove that it is prime, well, it's not easy for us, but there does exist a proof that it is there is a way to prove in polynomial time that some given number is a prime number. Okay, so then once you have again a problem that is both NP and co-NP, and so again it got people thinking, and not very long ago people came up with a polynomial time algorithm for checking that a number is whether a number is prime or not. Okay, and integer factorization is the problem that people are working on now, right? Because a lot of public key cryptography depends on the ability to factorize integers, right? Or in other words, the security depends on the belief that integers cannot be factorized efficiently, right? But we can easily see that this is a problem that's in NP and co-NP. Okay, so suppose somebody tells you that integer is, here are the factors to the integer. Well, that is easily solvable in NP because you just have to guess the factors, right? So certainly in NP. If, let's say, somebody tells you it's not factorizable, well then they are saying that it is a prime number. And we already see that there's a polynomial time algorithm for verifying that something is prime. So again, integer factorization is another example which is both prime, both NP and co-NP. And again, people are really worried that as a result somebody might find an efficient algorithm. Okay. Obviously, a lot of people have been working on finding an efficient algorithm. They haven't found it yet. So maybe there is hope, or maybe there isn't. I don't know. Okay, so let's build out a little bit more structure. NP hard and NP complete. So you have this class of NP hard will define. Okay, a problem is NP hard if the availability of a polynomial solution to that problem will allow all NP problems to be solved in polynomial time. So in a sense, this is the hardest NP problem. Okay, because once you can solve, if you are able to solve this problem in polynomial time, then everything in NP can be solved in polynomial time. So we are saying the other way to think about this is as hard as any other problem, right? It's at least as hard as any other problem in NP. Okay, and NP hard doesn't necessarily mean that it is the problem itself is an NP. So there could be problems that are outside of NP, right? Such that a solution to those problems will still allow you to solve NP problems. So strictly speaking, NP hard just has an overlap with NP, and this intersection of NP hard and NP complete, NP and NP hard is the class of NP complete. And what that means is that if you have a solution to any one problem here, okay, that solution can be used to solve every problem in NP in efficiently, right? So there is, if you have a polynomial time solution to any single NP complete problem, that will allow you to solve all NP problems in polynomial time. Okay, so that makes the complexity class hierarchy look like this. So the way, like I just said, the way we think about hardness of problems is by trying to reduce one problem to another problem. That is, I have a solution for, suppose I have a solution for a problem B, okay? Then I can use the solution to solve a problem A if I could transform an instance of problem A into an instance of problem B. Okay, so this is the notion of polynomial time reduction. So we want to reduce, we want to say that the two problems have similar levels of difficulty if I'm able to take one problem and transform it into polynomial time into another problem. Okay. So most of the proofs in, or rather every proof in NP completeness involves this type of reduction, right? You will show, for instance, to prove that some problem is NP complete, you will show that any NP problem can be converted, can be reduced to this NP complete problem, or you can take some other, a single NP complete problem and show that that can be converted or reduced to the problem that you want to prove to be NP complete. Okay? So let's never forget the direction. You need to, if you want to say that A is a hard problem, right? Well, then this is not. So what you want to do here is that this type of a proof, you're basically showing that B is a hard problem. Okay, you're not showing that A is a hard problem. Okay, what you're saying is that give me an arbitrary NP problem A, I can convert it into this problem B. Okay, and therefore, if ever I have a good solution for B, then I have a solution for A because I can first convert A into B, and then I can use this solution that you have for B. Okay, so that's why we need to be clear about what the direction is and what is it that we are reducing to what. Okay, so the question is, how do you get started? Okay, a particular NP problem A is given to you. Well, then you can think of a way to reduce that to B, right? So if I give you, satisfiability and ask you to reduce it to, some other problem, you can think of, okay, given problem A, I can reduce it to problem B. But if you want a proof that works for where A can be any NP problem, that seems hard because we just don't know how to give a construction for an arbitrary problem to another problem. Okay. However, if you already knew an NP complete problem, then it is easy. Then you take an NP complete problem A, and then you say that, okay, this problem B that I want to prove as NP complete can be used to solve this known NP complete problem. So this way, I have this mapping. So I can reduce all of NP to problem A, which I now reduce to problem B. Okay? So the proof, to prove that B is NP complete, the only thing I need to do is to pick a known NP complete problem. Okay? So, because it's a known NP complete problem, that means somebody has already proved that any problem in NP can be converted into this problem A. Okay? Now you prove that I can convert A into problem B. Now you have this path to go from any problem in NP to B. So once again, when you prove that, when you establish the polynomial type reduction from A to B, that means that I can take any problem here and in polynomial time convert it into an instance of B, which means that if I have an efficient solution for B, again efficient always in this context means polynomial time, right? So if I have an efficient solution for B, then I can also have an efficient solution for any problem in NP. So, well, the interesting question is how do you get started, right? If somebody has proved something to be NP complete, then you can go from there. But how do you start the process, right? And so the first NP complete problem is actually the satisfiability problem. Okay, and it was shown to be NP complete by Stephen Cook and Leonid Levin. These works are totally independent, right? So one was done in former Soviet Union, so it's sort of they were in their own world. So even though this was done in 1970 here, people were working on it independently in the Soviet Union. So anyway, so Stephen Cook was in the math department and he wasn't given tenure. He said, you are not productive enough. You're not producing enough papers. Well, anyway, so I guess he had the last laugh like 10 years later. Okay, so I'm not going to go into exactly how this proof goes, but I think we can give enough of the intuition. Okay, so how do you reduce arbitrary NP problem to SAT? So the basic idea is, well, you start with the formulation of the problem. Okay, so what is NP? NP is formulated using non-deterministic Turing machines. So the way you prove that satisfiability is NP complete is by saying, okay, give me this transition function for this non-deterministic Turing function, Turing machine, right? There is a transition function that's specified, right? There's a delta, right? Suppose I can take this transition function and convert it into a Boolean formula, right? Or I can say, here's a Boolean formula such that if this non-deterministic Turing machine accepts this input, then this corresponding Boolean formula is satisfiable. Okay, so if I can make that connection, then well, I have my NP completeness proof, right? So the basic idea is to simply start with this transition function. So the way to think about it is that thinking about arbitrary problems and reducing them to satisfiability is hard, but basically what we are doing here is we are saying, okay, you might have an arbitrary problem, at least you have to express it using in the form of a program. Then I can take this program and I can do something with it and show that this program can be, I can do some construction given this concrete program. Okay, that's exactly what's happening here. So the program is in the form of a non-deterministic Turing machine, and then I'm going to take this program and munge it and come up with a formula. So the way we are going to do this is, well, what does the Turing machine have? The Turing machine has tape contents, and the satisfiability problem, I have the only way to quote unquote remember things is using these Boolean variables, right? So what I'm going to do is I'm going to encode the content of the tape using a Boolean formula, okay? Using Boolean variables. Well, I know that if the Turing machine accepts it in polynomial time, then you could have only written polynomial amount of things on the tape, right? There isn't a way to write anything more than you can at most write one thing on a tape in one cycle, right? So if the problem is solved by the Turing machine in polynomial time, it could have written only polynomial number of entries on the table on the tape, which means that I only need a polynomial number of Boolean variables to encode the value that's stored on the tape, right? At any one instant. But of course, what I'm interested in is not in talking about the state of the Turing machine at one point. I'm going to talk about whether the Turing machine eventually accepts it, right? Which means that I need to talk about the path that the Turing machine goes through, which means that the Turing machine starts with some state on the tape, and then in the next cycle it has a different state on the tape, and then on the next cycle it has yet another state on the tape, and so on, right? But once again, I can say if I stop in polynomial time, then there are only polynomial number of distinct contents on the tape. So what I need to say now is I can say that there is this P of n square amount of state, okay? P of n state at any time, but there are P of n cycles. So if you want to encode the history of all the states on the tape at any time during the operation of this non-deterministic Turing machine, then I will still need only P of n square, and obviously the square of a polynomial is a polynomial, right? So I can encode the content of the tape in polynomial time, okay? And once you can do that, I will leave it at this point in terms of how you can encode the transitions themselves as a Boolean formula, okay? We'll do some exercise later on in homework, which doesn't get to Turing machines, but at least we will try to look at finite state machines, right? And for finite state machines, how can you encode acceptance by a finite state machine as a Boolean formula, okay? So that we will be able to do, and that'll give us some intuition as to how this construction was done, okay? Again, it's a very, very ingenious construction. To come up with a construction is, of course, extremely hard. Once construction has been done, it's actually quite easy for us to follow. Okay? But it's actually a very, very deep result. So, as a result, we come back to our cartoon, and again, remember, what did you want to say? Well, you wanted to say Right. This is what you wanted to say, right? I can't find an efficient algorithm because there isn't any. Unfortunately, couldn't do that, but instead you are able to at least say, well, it's not that I am the only stupid person in the world. All these famous people are also equally stupid because they are not going to be able to solve these problems. And the important thing to remember is that it's not that these people have all been working on the problem that's of interest to you, right? Because if that was the case, well, there isn't such a long line of people, right? Because your boss asks you to solve the problem because presumably it's something specific to your business, so not necessarily everybody in the world is working on the problem. But because of this connection between all these NP problems, they have been working on different problems that are hard, but are all polynomially reducible to the problem that you're interested in. And therefore you're able to, draw on the collective wisdom and collective experience and still say, well, none of them are able to solve this problem efficiently. Okay, so now what we are going to do for the rest of this lecture is to talk about some hard problems and